Hello everybody. In this video we're going to discuss or talk about the answer to the last question that we discussed in the previous video, is how can we determine the dimensionless parameters. So I hope by now we are convinced that the dimensionless parameters are important. They are very useful. They save us a lot of time, and they make dealing with equations much easier and more meaningful. And now the question is how to define these dimensionless parameters. So there are many methods that are used to develop these dimensionless parameters, but the one that we are going to discuss is called the Buckingham pi theorem. Buckingham pi theorem states that if there is a physically meaningful equation, so this is important. It's not just any random variables that will be grouped into dimensionless numbers or dimensionless groups. It has to be parameters that are part of a physically meaningful equation that has number of m physical variables. So this is the number of variables we have, including the variable that we are studying, that you are interested in, and the parameters affecting this variable. Then the original equation, which is to be written as a function of each one of these parameters separately, can be rewritten in terms of dimensionless parameters that we call pi 1, pi 2, and pi 3 until pi number p. Okay, that's why you call it pi theorem, because we initially call the dimensionless groups pi's. And the number of dimensionless groups equals m minus n, where m is the number of variables, as we said, and the n is the number of physical dimensions, which is L, M, T, and T, whatever. This is very useful because it helps us set the number of the dimensionless parameters and know how many parameters, dimensionless groups that we will have, even if we don't know the final form of the equation. And as we said last time, this is very useful in reducing the number of variables to make the experimental data or experiments that will be done small or less in number. So the steps of creating the pi groups is listed here. It's going to be hard to understand these steps without an example, so I'm going to skip this slide now, and I'm going to go back to this slide as we move forward with the steps of the example that we are going to see. So the example is going to be very relevant to what we studied before, and it's going to be an introduction to the next chapter. So one of the things that we discussed at the end of chapter 5 is in the modified Bernoulli equation, or the general energy equation, is the losses. And we said that there is a term that is called HL, and it represents the loss of energy due to the viscous forces. So it can be expressed in terms of length, which is HL, or we can express it as pressure drop. So both are things that represent the same thing. So when we have losses, it will be observed in the pressure loss. So now we are going to discuss the factors or see how we can create dimensionless groups for this delta PL, which is the pressure losses. So we know from experiments that the pressure drop, and this is per unit length, and this is important, so it's the pressure drop per unit length. It's function of some parameters: the density, the viscosity, the diameter of the pipe, the surface roughness. Surface roughness is a new term that we will see now, but surface roughness is something that relates to the material from which the pipe is made. So no matter how smooth the inner surface of the pipe is, if we zoom in closely to the surface, you'll see that there are some irregularities. It's not like smooth, perfectly smooth surface. There are some irregularities, and the height or the average height of this irregularities is what we call the epsilon, or the surface roughness. So it's the average length. Okay, so this is something that also affects the pressure drop. The velocity of the flow also affects the pressure drop. So we can write the relation as delta PL is a function of these 5 parameters. So it's exactly similar to what we mentioned in the previous video, that X is function of A, B, C, D, and E. So it's the exact same thing. So we need to combine them into dimensionless groups. So the first thing to do is to put them in, or to list all the parameters that we have, the variables and the parameter we are studying, and to put the units or the dimensions of each one of them, the dimensions. For instance, diameter has dimensions of length, velocity LT minus 1, density ML minus 3, and so on. And this is, if we go back to the steps, this is, this is step number 1, to write the dimensions of all variables and calculate the number of dimensions and the number of variables. So this is the number of variables here is 6. These are the 6 variables. And if we check the number of dimensions, we have L, T, M. That's it. We don't have anything else. So we have 3 dimensions. So according to the pi theorem, we have m minus n groups, which is 6 minus 3. So we'll have 3 dimensionless groups. And for these 3 dimensionless groups, we will be able to, or we still don't know the shapes of these dimensionless groups, and this is what we're going to do. But we know that we can reduce these 6 variables to 3, which is a very, very good thing. Okay. So now the question is, how can we set these dimensions or determine these dimensions? So the first thing is, is to select n of the variables. So we have n equals 3. So we have from these 6 variables, we will pick 3. It's n variables. 3 of these 6 to be what we call repeating variables. We call them repeating variables because they will appear in all the pi groups originally, in the original shape, or the first shape. The first step in setting the dimensionless groups is to have these repeating variables. So we have 7 and we need to pick 3 of them. We don't have any clue for now which 3 we'll pick. Shall we pick the du rho, mu delta p epsilon, d epsilon mu? We have like a very, very big number of options. So to reduce the number of options we have and to make them or make the choice easy for us, we have some criteria that we can follow. So the first is that none of the repeating variables can be dimensionless. So if you have mole fraction, mass fraction, efficiency, anything that has no dimensions, it's not it cannot be used as a dimensionless groups. The second is that we cannot have 2 dimensionless groups with the same dimensions. So in our case here, we have the diameter and epsilon. Both have the same dimension, so we cannot pick both. So either we'll pick diameter or epsilon. Okay, so I'll pick the diameter for now. The third is that the repeating variables should represent different aspects of the system. So one should represent the flow property, one should represent the flow property, and one should represent the dimension. So if we look at the parameters here, we have rho and mu both represent fluid properties, so we cannot pick both of them. We'll pick one of them. This is the only parameter that represents a flow property. Okay. Another flow property would be mass flow rate, would be volumetric flow rate, something like this. The diameter already represents the dimension of system, so we will pick D, one of these 2, so it's rho or mu. And now, we have U and delta PL. We need to pick one of them. There is one last criteria. I don't have it in the slides here, but the last criteria that is going to be helpful is that we cannot pick the dependent variable as a repeating variable. So the dependent variable according to this equation is delta PL. It's dependent on the rest of them, so I cannot pick delta PL. So this will narrow the options to only one option, or to few options, either D or epsilon. So we'll pick D, rho or mu, so we'll pick rho, and U or delta P. We cannot pick delta P, so we have only U left. So we'll pick the diameter, density, and the U. Okay. Of course, you have some flexibility. You can pick mu instead of rho. You can pick epsilon instead of d. It's fine. But this is what we're going to go with now. And of course, if you pick different repeating variables, the shape of the dimensionless groups will be different at the end. But at the end of the day, we are going with, or this is a method for picking the or developing the dimensionless groups, and then the experiments will show if they are good dimensionless groups or not. And also there's one important point here, is that we said that the dimensionless groups have physical meaning, and this is why different options have been studied, and what we're going to go through is the best option, which is the development of dimensionless groups that have physical meaning, and they have something to say about the system that we are dealing with. So after picking these repeating variables, we need to see how these will be repeated in the system. So the shape of the pi group is the 3 repeating variables, each is raised to a power, and then it's multiplied by one of the non-repeating variables. So we have now the variables split into 2 categories: the repeating variables and the non-repeating variables. So each dimensionless group contains the 3 repeating variables, each raised to a power, and one of the non-repeating variables. So we will have 3 non-repeating variables, so we will have 3 dimensionless groups, one with mu, one with epsilon, one with delta p, and each one of them is multiplied by rho d and u. Each one is raised to a power. So if you know the values of the powers, we will know the shape of the dimensionless group. So this is simply what we want to do. So to get or to find a way to calculate the powers is very, very simple. It's based on the same idea that these pi groups are dimensionless groups, which means that the dimensions of this is m power 0, l power 0, t power 0, and we already know the dimensions of each one of them. So we can say that the m power 0, l power 0, t power 0 equals the density, which is ml power minus 3 power a, diameter, which is l power b, velocity lt power minus 1 power c, and then the viscosity, which is ml power minus 1 t minus 1. And now we will group the m's together, the l's together, and the t's together, and then we will see what are the values of a, b, and c that will make the right hand side equals to the left hand side. So for m power 0, we have m power a plus 1, so it's a plus 1 is 0. For L, we have negative 3a plus b plus c minus 1 is 0. And for t, we have negative c minus 1 is 0. So we will have 3 equations and 3 unknowns. And simply by solving these equations, you know that a is minus 1, c is minus 1, and by substituting here, you will find that b is also minus 1. And by substituting these 3 numbers in the first pi group, you will see that it is mu over rho ud. So it's simple algebra. It's nothing complicated here. Okay, we will follow the same procedure for the second pi group, and by doing the same thing, it's a very, very simple process. I'm not going to repeat it. So you'll find that the second pi group is epsilon over d. The third pi group is going to be delta p l d over rho u square. So this is what we need, is to group these 6 variables into 3 dimensionless groups, and this is what we did. There is one thing you need to keep in mind, is that all these dimensionless groups are dimensionless. Okay, so mu over rho ud has no dimensions, and if you flip it or put the reciprocal of this, it's going to be rho ud over mu, which is also dimensionless. Okay, so it's not necessarily that the process produced this mu over rho ud is to go with this mu over rho ud. What we use is rho ud over mu, and the reason for this is that the mu over rho ud will have very, very small values. It's going to be from 10 power minus 6, 10 power minus 5 to 10 power minus 1. It may be 10 power minus 7 either. I mean, it's a very, very small number. So dealing with it is not is not going to be mathematically easy or good to deal with it mathematically. So we prefer to go with the reciprocal because this makes the numbers bigger, and it makes dealing with it easier. And this is what everybody is using for this dimensionless group. So at the end of the day, we have a dimensionless group that contains this delta PL, which you are interested in, and other two dimensionless groups. So we can write the equation instead of delta PL is a function of these 5 variables. We have pi 3, which is this, as a function of the two dimensionless groups. Okay, so this makes the process much easier for doing the experiments and for getting the shape of the function. One thing here, which is a very important thing, is the physical meaning of the dimensionless group. So the first is a very famous dimensionless group. So we'll see this inshallah in the next chapter in more details, but this is called Reynolds number. And if you look at the numerator, you have the density, which is the mass per unit volume, so it's a specific mass, multiplied by the velocity, multiplied by the diameter, which is a representation of the size of system. So as you get the numerator high, it means that it has high mass, high velocity, and high diameter. So it means that there is a lot of inertia. So this numerator represents the inertial forces, and the denominator represents the viscosity, which is the viscous forces. So if you have flow with high Reynolds number, it means that it has more inertia, much more inertia than the resistance to the flow, and vice versa. So this is a very important dimensionless group that we will see a lot later. This epsilon over T represents how big the roughness of the surface is relative to the diameter of the pipe. So it's called the roughness ratio. And the final one is delta P. It doesn't have a specific name, but it's delta PLD over rho U square. The rho U square over D, this thing is usually or commonly called the dynamic pressure. A way of another can be a representation of the flow work. Okay, so it's how much energy the fluid has while it's moving forward, or the energy that is moving the fluid forward relative to the this, and this is the losses. So these are the losses relative to the dynamic pressure. Okay, so it's how much energy is lost or pressure is lost relative to the pressure that the fluid has to move forward. So after setting the dimensionless groups, we have this relation. We know all the parameters in this equation, but we don't know this f. We don't know what is this function. Is it Reynolds number plus epsilon over d multiplied by each other, any other relation? This is what we can get experimentally, and this is what we will see inshallah in the next chapter. So if we know this function, we can get delta PL, because we're not interested in this dimensionless group by itself. We're interested in delta PL, so we can multiply this whole equation by rho U square over d. So it's going to be delta PL multiplied by rho U square over d multiplied by this function, and this is what we want to do. So the experiments that will be needed to get this relation are just for two parameters on one, or two variables on one parameter instead of 5 variables on one parameter, which is much more easier and more practical. And the practicality is important here, because we are not only studying the effect of density or viscosity, we are studying the combined effect. So it doesn't matter if we change the density or the viscosity, and we don't have the problem of changing one and keeping the other constant, as we said before. So this is what we're going to see in details in the next video, how this function looks like and how we can use it to calculate the pressure drop and the head losses in internal flow in pipes or tubes. One last thing here is just a quick check on how the dimensionless parameters are useful. I put some numbers here for a flow: the specific gravity, the viscosity, the diameter, and the velocity, and I'm calculating Reynolds number for both systems of units, the SI and the US unit systems. And you can do the math yourself or revise the numbers that I have, but after you do the calculations, for both unit systems, and you can try it for CGS system as well. You'll find that the number is the same. It's 17,780, and here it's also 17,780. So you're getting the same number no matter what is the type of system you're dealing with. And this also confirms what we mentioned before, that the dimensionless groups are only defined by the quantity without the need of a unit to fully define this this dimensionless number. So by this we end this chapter. And inshallah in the next video we'll start with chapter number 8, which is about the flow in internal flow in pipes and tubes, and how to calculate the pressure drop using and how the relation that we discussed here will be or will look like, inshallah. So I'll see you then, inshallah. Goodbye.